All right. So welcome everybody. I'm here today to host Northeastern University's Quantum Matter Seminar. Today we have Natasha Perkins from the University of Minnesota, and she's going to be talking about phonon dynamics in Kitaev spin liquids. And as usual, Natalie prefers to be interrupted during the talk if you have any questions. So just raise your hand and I will let Natalia know that we have a question. And with that, please, Natalia, take it away.
Thanks a lot for the introduction. Thanks everybody for joining this seminar, and good time of the day. I see some good friends from Europe, so probably it's already late. So thanks a lot for joining to everybody. Okay, so I'm going to talk about phonon dynamics, and I will try to explain what we did and also why we think it's important to really know the microscopic nature of the coupling of the excitation in quantum spin liquid, in our case, Kitaev spin liquid, to phonons, which are present in all real materials. The talk is based on two work, one finished and one being in preparation. So the first work was published last year with Min Xinye, who we started this work when she was still in the University of Minnesota, but now she's a postdoc in KITP, and Rafael Fernandez from University of Minnesota. And the continuation of this work, where basically we take the flux contribution, that's what actually make Kitaev spin liquid very different from many other systems. So we take this flux contribution into phonon dynamics into account, and basically we show that the observables which you can obtain can be drastically different at finite temperature, where this flux contribution they are very important. Okay, so I'm sure nobody needs introduction, but let me start from somewhere. So quantum spin liquid, it's the state of interacting spins, which breaks no rotational or translational symmetry. And what is important that there is no local order in this state. And therefore, quantum spin liquid is certainly the phase beyond the Landau paradigm, which basically order parameter can describe any type of magnetic order. And there's many things what we discuss nowadays. The discussion of quantum spin liquid starts from Anderson's work about resonance valence bond, where he suggests that it can be a state which cannot be written as a product state. And that's probably one of the main characteristics of the quantum spin liquid. So in that case, this resonance valence bond state, when you have a spin singlet covering triangle lattice. So at the beginning, he was actually suggesting this resonance valence bond state to describe the ground state of Heisenberg antiferromagnet on triangle lattice. And despite the fact that this idea was wrong, because nowadays we all know that the ground state of the quantum Heisenberg model on triangle lattice is the ordered states with 120 degrees ordering, that work actually started a lot of discussion about the possibility of these states, and quantum spin liquids are among them. Quantum Hall is another type of these states. So what do we need to have a quantum spin liquid state? We need, first of all, the extensive number of states with a very, very low energy. Basically, it's great if they are all degenerate, but if they are very close in energy, then in a variational sense, they can give us all this classical manifold of quasi-degenerate states. And then we need a strong resonance in tunneling between these states to form these states. And in that case, the ground state of quantum spin liquid cannot be written as a product state, but in fact, it is a superposition of the wave function of different covering, for example, of spin singlet in this case. Okay, and starting from 1973, a long time passed, and nowadays we know that there are many different quantum spin liquid states. And what is also very important that they have non-universal manifestation. And here is the list. Perhaps it's not a complete list, but nowadays we know about the gap topological quantum spin liquids, which are characterized by topological order. And then among of them, there are different kinds of quantum dimer model and toric code mode, which was proposed also by Kitaev. There are quantum spin liquids with a spin-on Fermi surface, which perhaps can be realized in triangle lattices. And nowadays, there is a whole variety of Kitaev quantum spin liquids. And I wrote here gapless because I'm going to talk about gapless quantum spin liquids, but they can be gapped or gapless depending on the parameters of this, on the couplings of this Kitaev model. And they can be in 2 dimensions, they can be in 3 dimensions. And what is amazing that all these Kitaev models, they are exactly solvable. And therefore, for us theorists, it's a very good playground because many things can be done almost analytically. Okay. So basically, these are the characteristics of this quantum spin liquid. So the most accepted definition is still very negative. So you say that quantum spin liquid is a state which has no order, but if you want to find it both numerically, analytically, or experimentally, you need to have some positive definition. And in that sense, one can say that quantum spin liquids are characterized by topological order, long-range entanglement, and fractionalized excitations. So the topological order, it's usually associated with the topological entanglement entropy and topological ground state degeneracy. These 2 concepts nowadays, once again, are very well known, but they are not very effective in experiment because it will be difficult to imagine that you can prepare a beautiful 2-dimensional quantum spin liquid and then put it first on the torus and then to the sphere and basically compare the degeneracy of the ground state. So the effective way to observe quantum spin liquid in experiment, especially in experiment, this way is based on the presence of fractionalized excitations. And what is also important that this fractionalized excitation can have exotic statistics, or for example, they can have anionic statistics. So the focus of my talk will be on the Kitaev model on the honeycomb lattice, this original model, the 2D model. And once again, this model is nowadays very widely discussed. So basically what you have a honeycomb lattice, and on each of the bond, only one component of spin is interacting. So already from the classical perspective, it's clear that this model is frustrated because you cannot satisfy this Eigen interaction on all the bonds simultaneously. But I think what is even more amazing that this model has exact solution, and this exact solution is a quantum spin liquid. So I think the genius of Kitaev was not only about the proposing this model, but also realizing how to solve this model in the most visual way. Because if you think in the spin representation, if you think in terms of the spin variables, and you look to these quantum spin liquid states, then you have kind of fluctuating sea of the spins, and it's very difficult to say something definite about this exact quantum spin liquid ground state. Kitaev solved this model using Majorana fermion representation, and in this representation, basically the fractionalized excitations of spins, so the usual magnons, they fractionalize into fluxes, and the Majoranas, 2 very different type of fractionalized excitation, because Majorana fermions, they form dispersive modes, so they are itinerant particles, and the flux degrees of freedom, they are gapped and static, and therefore one can actually find the solution both in the ground state and in the excited state by fixing certain flux configurations. Once again, I will talk about this model in a moment, but another important piece in the progress of studying Kitaev materials was actually the very famous by now paper by Jackelli and Khaliulin, where they actually proposed the way where to look for this Kitaev spin liquid. That it can be the whole class of motor insulators with strong spin orbit coupling, where this type of model can be realized. And starting from this seminal paper, a lot of experimental study were indeed performed. And nowadays we have the whole variety of candidate materials in 2D. So I think by today, my list here is already kind of outdated because there are more and more new materials. but the study studied from different kind of honeycomb iridates, and then one of the most famous candidate for Kitaev spin liquid is the Alpha Rhutinate. Once again, nowadays, everybody knows about this compound. So most of them, except this hydrogen intercalated iridate, where disorder play a very important role, all of this compound order, but the ordering temperature, Niel temperature, is always significantly lower than the Curie-Weiss temperature. So these systems are very frustrated, and this order can be easily destroyed not only by temperature, but also by magnetic field. So all these materials are suggested to be at least proximate to quantum spin liquid, and therefore many properties of quantum spin liquid, especially in the excitation spectrum, in the dynamics, can be observed in the real materials. And therefore, nowadays, basically, there are different dynamical probes like Raman scattering, neutron scattering, terahertz spectroscopy, different type of spectroscopy where people are looking for the excitations of these materials at finer temperatures and try to extract the features of Majorana fermions in the spectrum, which would be characteristic for Kitaev spin liquid. All of these measurements, they're of course are very important, but one measurement still not completely, it's not still completely settled question. If the question is if thermal Hall effect was or not observed in the ruthenium chloride. But in 2018, the group of Matsuda basically showed that if they measure thermal Hall effect in this material, then they see a quantized plateau in kappa xy when they apply a magnetic field. So, so here are the results of the experiment, and you can see that in the tilted field, so here they had some field H in the AC plane with the different angles. So what they present in their paper is that plateau in kappa xy is observed as a function of field, and basically not only that, but it's actually quantized to the value which one would expect from the chiral-Majorana mode in the Kitaev spin liquid. So if that's true, and that is kind of confirmed, that would be the best proof that this ruthenium chloride is indeed the proximate material to the Kitaev spin liquid. So after this paper, they also study in this subsequent paper by Yokoi, it's the same group, they actually showed that this plateau can be observed even in the plane, so without this perpendicular component along C-axis. But also if you change the direction of the field, so it has significant angular dependence, this kappa xy is changing sign, and that is presented on this figure. And in that case, that would indicate that chair number is actually changing the sign when the field is changing the sign. So everything feels into a very coherent picture. Once again, we would love to see the confirmation of these results, but in principle, that was a very interesting measurement. What was also important, it was two papers, once again in 2018, where it was a theoretical papers which were trying to understand if indeed this quantization plateau can be observed in these compounds. And the conclusion of these two papers were very similar, and basically that without contribution of the phonons, and also in these compounds, kappa XX, the longitudinal thermal conductivity is significantly larger than the transverse thermal conductivity, that basically the conclusion from these theory papers that you need to have a very strong spin-phonon coupling. In that case, when the phonons are coupled to H mode, that's the only way when you can observe quantized thermal Hall effect. And starting from this, we were actually thinking that if this is indeed the case, then the spin-phonon coupling in these materials is very important, and we need to understand better its microscopic origin, but also can we use the phonon dynamics by itself to say something about the underlying quantum spin liquid state? So that was the motivation for our study. And basically, that's our suggestion that quantum spin liquid can be identified. There are observables which carry these characteristics. And for that, we need to look for renormalization of phonon spectrum, but also to the lifetime of the phonons. And both observable will reflect the underlying excitation of the quantum spin liquid. So, so far we identify 3 different type of observables. It's a sound attenuation, phonon Hall viscosity, and phonomagnetic effects. But we have some results only for the first 2 for the moment, and that would be the focus of my talk. So about the phonomagnetic effects, kind of something very similar to magneto-optical effects, like a Faraday effect, can also be observed in the Kitaev spin liquid. Okay, so this is basically the outline of my talk. I will present the model, then I will discuss how we describe phonons, and we will be only talking about the acoustic phonons today, and what is characteristic of this Majorana-Fermion phonon coupling vertices, and basically by the end of the talk, what are the observables and how we can compute them theoretically. Before I go on, so this is the end of my introduction. Are there any questions? Okay, so please stop me whenever something is not clear or you want some clarification. So this is the model which we consider.
Can I maybe just ask this question as this?
Sure.
My understanding of the work of Himeroff and Leon Valens was not so much that one needs phonons to see this composition, but rather the question was whether coupling to phonons would destroy composition, because composition would exist in pure electronic material. And the danger
Really, I can barely hear you.
And my understanding was that the claim was just that because of particular features of in coupling, quantization is not destroyed, or maybe slightly destroyed, but mainly remains. So is it really?
No, I think they did 2 statements. So first statement is that in the presence of coupling, again about the acoustic phonons to the H mode, so to the chiral H mode, which will produce this, that the quantization will remain. But second, if you want to realize this realistic situation, especially when you need to also say that kappa XX is very large. So basically, the whole angle is very small. The whole angle is the ratio between kappa XY to kappa XX. So the whole angle is very small, and you need to understand, so it's clear that phonons plays a role. So, and basically, what they did about the, what they were saying is that the ballistic transport are destroyed by the phonons, but in order to have quantization, you still need to have this coupling. So basically there were 2 statements. First, that the quantization will remain, and second, it can only be observed. They have, especially in the paper of Barnes, if you remember, there were all these discussion about the different phonon and fermionic temperatures, that in order that it can be observed, then you need to have a strong spin-orbit coupling. So those 2 statements there.
Okay, very good.
Okay, so here is the model. Our model has 3 parts. The part which describes spins, the part which describes phonons, and the coupling terms. So since we're interested both in Hall viscosity and in attenuation, we also keep this kappa term in the Kitaev model. So it's extended Kitaev model, where this free spin interaction actually mimic the effect of magnetic field. So the time reversal symmetry is broken in the presence of kappa, but the system remains exactly solvable. So the second term is the Hamiltonian for phonons. It has kinetic part and it has elastic part. And we will treat phonons, the acoustic phonons, in the long wave limit. So basically we will treat phonons as some sort of elastic media. either with time reversal or with time reversal symmetry breaking. And then there is a coupling term. And once again, the origin of this coupling term comes from the fact that if you start moving ions, so due to phonon vibration, then the Kitaev coupling on the bond is changing, and that's provides the coupling. I will just talk about this in a moment in more details. So spin part. Once again, very, very briefly, the exact solution is based on the fact that for this model, we can define a macroscopic number of conserved quantities, and these conserved quantities are plaquette operator, which on each plaquette you write by a product of 6 spin operators, and on each side you take the component of outgoing, the spin component corresponding to the type of outgoing bond. So one can show that each of these plaquette operator commute with the Hamiltonian, and they also commute with each other. So the eigenvalues for these plaquette operators are ±1. When it's +1, we say that there are no flux. And when they are -1, we say that there is a flux on a given hexagon. And one can think about the phase like in the Aharonov bond effect for the Majorana fermions. Okay, so the solution, the way how solution was obtained by Kitaev is to represent each spins with the help of 4 Majorana fermions. 3 Majorana fermions will carry the upper index alpha, which corresponds to the component of the spin, x, y, z. And then it would be 1 Ci Majorana fermions, which would be some sort of charge, but you should remember that we are all the time speaking about the insulators. So once you go to this Majorana fermion description, you can rewrite this Hamiltonian with the help of these Majorana fermions. And in this case, you need to remember that the Hilbert space is extended, it's enlarged, and basically whatever you compute, you need to be sure that you're computing with the true physical states, so the projection needs to be done. But in Kitaev model, the projection to the physical space can be done exactly. So once you introduce Majorana fermion on each of the bonds, you can introduce this U link variable, which corresponds to actually Z2 gauge variable. And you can see that since this plaquette operator can be written as a product of these U operators, then these U operators commute with the Hamiltonian, so it's also a conserved quantity. So now everything is very simple. You rewrite the Hamiltonian, and in each set of these link variables, you distribute these link variables, then you determine what is the physical flux, what is the physical values of W corresponding to the set of U variables. You just have a hopping Hamiltonian, and that is the essence of the exact solution of the Kitaev model. So now you just look to each of the ground states. You try to find what is the lowest energy ground state, and you found that the ground state is such when all the plaquette operators are equal to 1, and basically there are no fluxes. So 0 flux is the ground state of the Kitaev model. Here what I plot, so in the ground state, you can plot the spectrum for Majorana fermions and the density of states for Majorana fermions. And these couplings J alpha, which is the Kitaev couplings on different bonds, they can be either isotropic, this case D, which we are going to discuss. And in this case, we see that Majorana fermions has a spectrum which is exactly identical to one in the graphene. And there are a lot of analogies in the spectroscopic properties of the Kitaev spin liquid when the probe is coupled to Majorana fermions at low temperature. There are some analogies with graphene. So, but you can also see here this Van Hoff singularity, and you see how the density of states grow linearly at very low omega. So you have a vanishing density of states at omega going to 0, the same as in graphene. So when you have anisotropic couplings, then in fact you can have very different spectrum. And in many cases, when you are far away from the isotropic point, the gap in the excitation spectrum can open. But once again, my focus is on this isotropic case today. So what is also important that what is happening at finite temperature. So at the ground, at a very low temperature at T equals 0, we know that the ground state is flux 0 state. But when temperature grows, there are enough thermal excitation to excite fluxes. And basically, we are going from the 0 flux to thermally excited flux sectors. And once you have these thermally excited flux sectors, you know that the translational symmetry is broken, and your Majorana fermions are losing these Dirac cones and this beautiful structure which I showed on the last plot. So thermal fluxes works like disorder for Majorana fermions. And there are two energy scales, which was shown by a group of Matomi. The low energy scale, when the fluxes proliferate, basically they start being occupied starting from 0 temperature as soon as the temperature is growing. But then there is an energy scale of the order of 0.1. Then you can consider the situation as a random flux configuration. So fluxes that are already proliferate. And then there is a high temperature scale when you go to the paramagnetic states. And then in this case, both degrees of freedom, fluxes and Majorana fermions, are already fully excited. So then this is just the usual conventional paramagnetic state. So the effect of magnetic field, which will be important for us, which we describe with the help of this kappa term, which in terms of Majorana fermions is nothing else as in the pure Kitaev model, we have only nearest neighbor hopping of the Majorana fermions. But once we introduce this kappa term, we introduce the second neighbor hopping terms. This model become very similar to the Haldane model, and it's known when the time reversal symmetry is broken, the gap is open in the Dirac points, and one can find what is the size of this gap. So this is basically the minimum knowledge about Kitaev model, which we are going to use in our calculation. So once we do this, if we're in the 0 flux sector, then we diagonalize our Hamiltonian. We can do it in the momentum space because we have translational invariance, and then we can obtain the fermionic propagator. So we can go from Majorana fermions to complex fermions, and then basically we can describe all the excitation in the system with our fermionic propagators. The situation is slightly more complex when we have fluxes, because as I said, the time reversal symmetry is broken, and therefore we need to diagonalize our Kitaev Hamiltonian in the real space. But this can be done. Once again, the suggestion how it should be done was already suggested by Alexei Kitaev in his original paper. You need to use single value decomposition, and basically you can obtain the spectrum of Majorana fermions as the eigenmodes from E1 to En. And the only thing what you need to change your formulation and to do all the formulation on the discrete language. But other than that, everything is the same. You just use this eigenmodes basis instead of the spectrum in the momentum space which you had before. So finally, and another part which contributes in the whole story are phonons, how we describe the phonons. So as I said, we are interested only in the low energy phonon excitation, lattice excitation, and they are described by acoustic phonons. And the idea is that let's describe them in the long wave limit. So in that case, we can think about the action for the phonons written in this particular form, where C is the elastic moduli and Eij are the strain tensors. So this is once again the straightforward problem on the phonons on the honeycomb lattice. We can obtain the eigenmodes for the phonons, and these are the longitudinal and transverse acoustic models. So that determines their polarization, and basically we can obtain the spectrum. So the transverse mode, as we know already from Ashkev-Mermin, has the lower energy, so the transverse velocity is usually lower than longitudinal one. Okay, so now we have description for the phonons. this is the description of the phonons when the time reversal symmetry is present, and I will talk about how we describe phonons when the time reversal symmetry is broken later. So now the Majorana fermion coupling, so one can do in two different ways. So one can do this physical derivation based on the fact that the coupling between spin ions is changing when we have magnetic elastic coupling, or we can start from the symmetry channel and basically do the symmetry analysis. So here we have C3V symmetry for Kitaev model. So basically we will have two symmetry channels, A1 symmetry channel and E2 symmetry channel, so this doublet. And what we need to rewrite this coupling Hamiltonian using this irreducible representation as it's done here. And what we showed, and let me skip these details, that the dominant contribution into the scattering is actually come from the E2 channel. So because in the A1 channel, there will be some additional smallness in terms of the Majorana fermion K numbers. So, okay, so now we perform the Fourier transform, and now we have this form of Majorana fermion phonon vertices, lambda K and lambda, these two lambdas with a parallel and perpendicular, so for longitudinal and transfer, to coupling between the longitudinal and transverse phonon modes to the Majorana fermions. And once again, you can see that here we keep only the dominant contribution. So we have already smallness coming from the Q. Q is the phonon number, and therefore what comes from the Majorana fermions is just a constant contribution. So our vertices in our calculations are linear in phonon momentum number. Okay? What else is important to see here is that there is angular dependence, which depends on the polarization of the phonons already in the expression for the vertex. So the vertices have angular dependence, and they are not constant depending on what is your phonon direction. Okay. Once again, this expression.
What are tau here?
So tau here is auxiliary Pauli matrices, which just help because, okay, I probably skipped this. Sorry. So basically here, the spin Hamiltonian for Majorana fermions can be written in terms of in the matrix form. And basically what we have here in these matrices can be written with the help of these auxiliary tau matrices like this, okay? So tau x and tau y are present both when time reversal symmetry is present and when it's broken, but this tau z is coupling to the gap which is opening in the presence of this kappa term. So these are just the matrices which allow us to write everything in the matrix form. Okay, so the complication comes when the translational symmetry is broken, and we cannot use momentum for Majorana fermions as good quantum numbers. So in that case, the translational symmetry for phonons are still there. So we can still describe phonons in the momentum space, but we need to describe Majorana fermions in the real space. So we need to formulate our vertices in this mixed representation. So once again, details are not important here. What is important that these vertices lambda q lm means that we have this is a vertex of coupling between the phonons in polarization, in this case longitudinal polarization with a wave vector q, to Majorana fermions eigenmodes, Lm eigenmodes of the Majorana fermions. So this is basically this mixed representation which we are going to use for finer temperatures. Okay? So now how we go to the observables, we have our phonon propagator. So this would be our bare phonon propagator, which we find just for the phonons on the honeycomb lattice. But now, due to the coupling to Majorana fermions, this propagator acquires self-energy, and this self-energy, phonon self-energy, basically that is responsible to the coupling to the phonon. So basically what you can see here, these two solid lines are green function for the Majorana fermions, and here we have a product of two vertices. So the structure of this one loop self-energy for the phonons will actually determine how we will be able to see the features from Majorana fermions in the phonon dynamics. For example, in the renormalization of spectrum, or in the change of lifetime of the phonons, or in the phonon Hall effect. Okay? So this is what I want to say, that this is actually the central quantity which we need to compute in our calculation, and that's what we are going to do, both at very low temperatures when we can assume that Kitaev model is in the ground state zero flux sector, and at finer temperature when we have to average over different flux configuration. And we will, following the work of Matomi, we will treat these flux degrees of freedom using Monte Carlo calculation. So basically that will be treated with the help of Monte Carlo. And the observables which we are looking for is the renormalization of the sound velocity. We will see that in the presence of kappa term, when time reversal symmetry is broken, we will have a mixing between transverse and longitudinal phonon modes, and that would be one of the observables of the thermal Hall effect. But also we will see that attenuation and absorption of sound wave of acoustic phonons would actually be a good measure of the type of excitation in the Kitaev spindle. So let me start with the sound attenuation, and this probe was heavily exploited in many systems, and it started, I don't know, more than 50, 60 years ago, when people were interested in theory of metal, and the sound attenuation was one of the most effective probe of the type of the Fermi surface before all this kind of ARPES study were available. And it's also play an important role in the study of superconductors. Whenever you have some phase transition, when, for example, system is going to the superconducting phase, the sound attenuation will significantly change its behavior. So let's see if sound attenuation is also characteristic, has some characteristic features in our case. So once again, what is the sound attenuation? We have acoustic wave. We can use some transducer and basically pump these acoustic waves into the sample. And then we can see that the amplitude of these waves, or the energy of these waves, will decay with the distance from the driving force. So the sound attenuation, the way how it's described, it can be associated with inverse of the phonon mean free path. So it can be written like this. But in fact, one can relate this coefficient to the imaginary part of the phonon self-energy. And we showed in our work that the diagonal terms in this phonon self-energy give the dominant contribution in this decay. Okay, so when we start thinking about scattering of the phonons or decay of the phonons in the excitation, we need to look what are the kinematic constraints. We can certainly formulate them in the zero flux sector when we have translational symmetry, because in that case, we have both energy and momentum conservations, because our Majorana fermions, they carry good momentum for them is still a good quantum number. So what is actually important is what is bigger or smaller, the sound velocity or the Fermi velocity. In most of the compounds, the Fermi velocity is larger than sound velocity. Okay, so however, it can be some cases where the ratio would be the opposite. So we will mostly, the results which I will be showing today would be for this first case, just because I have limited time. But in our future paper, you can also see all the results for the other limit. So if you consider this case, then you need to think. So the phonon is coming, so with the momentum q and with some energy vs q. And then if vs is smaller than vf, then it doesn't have enough energy to produce a pair of Majorana fermions. So the particle-particle channel is basically suppressed. And the only channel which you have is a particle-Hall channel. So you need to have already Majorana fermion in some state, occupied state. And then you can take this and move it to another unoccupied state. Okay? So it's clear that this channel will give contribution only at finer temperature because you need to have thermal occupation of Majorana fermion states. And once again, because the density of states for Majorana fermions in this cone is vanishingly small at small omega. So when you will be pumping up the temperature, when temperature will be increasing, your density of states will be larger, and therefore the number of scattering events will be larger, and the effect to sound attenuation will be stronger. So when Fermi velocity is smaller, the Fermi velocity actually is this characteristic of this Dirac cone. So when this is smaller than the sound velocity, then basically what you can show that the attenuation coefficient is mostly coming from the particle-particle channel, and everything, of course, it depends on the size of the phonon velocity. But then basically what it changed, once again, from the kinematic constraint, you see that the particle-particle channel, so basically this is this case when the Fermi velocity is smaller than the sound, then you can see that this particle-Hall channel become unsatisfiable with in terms of the kinematic constraints. Okay, so now basically what we did, we simply compute using the Matsubarra-Green function, we compute what is this polarization bubble. Okay, so let me skip the details of the calculation. This is very straightforward calculation, but what are the results? Let's first look to the case when we have a zero fluxes, and that means that we need to consider the temperature, which should be larger than VFQ. So we have already some occupation of the Majorana fermions, so we have some phase space, but it still should be smaller than the flux gap that fluxes does not need to be taken into account. So here are the expressions for imaginary part of the diagonal contribution to this polarization bubble, longitudinal and transverse. So what you need to see from that, okay? So first, what we need to see, and this is basically the relation, what you get for the sound attenuation coefficient for this different polarization. One thing very important, what you see is that you have this angular dependence here. So basically you start with the phonons, which has a spherical symmetry, more or less, or C6 symmetry, which is very high symmetry. And then because they scatter on the Majorana fermions with a Dirac-like spectrum, they acquire this anisotropic scattering. So the scattering will very much depend on the direction, and it will be some particular direction where it will vanish. So here we show this angular dependence for longitudinal scattering. So second thing, what is important, that this sound attenuation is proportional to the temperature. So it's proportionally linear to the temperature. So in that sense, it will be different from the sound attenuation due to anharmonic phonon fluctuation, which will give you T cube in the scattering. So, and then at low temperature, you can clearly distinguish what contribution comes from the Majorana fermions, linear in T, and what comes from the anharmonic terms. So once again, the fact that you get this linear in T term here comes from the fact that you need to have some Majorana fermions occupied. So basically, in short, you can think that it comes also from the statistics of occupation for the Majorana fermions. And then what is also important, that the phonon-Majorana fermion scattering is dominant, so one can perform the estimate what is the ratio between phonon-phonon scattering, once again, as I said, due to anharmonic terms, and these Majorana fermions or spin fermions scattering. And one can see that it's proportional to the ratio of the temperature to Vs over the La, which is the length unit for the lattice, and this quantity is significantly smaller than 1 at small temperature. So this is also the dominant contribution. Okay? So it can be observed. Okay, so now what I want first to see if I include temperature, if I go to larger and larger temperature, how my scattering will be changing. So what I show here on the right is t equals 0. So it's not t equals 0, it's very small t. Okay, t equals 0. Okay, sorry, it's probably, oops, sorry. I should not put here t equals 0, sorry. It's, so what I want to say that this result is the analytical result when I still can use the momentum space, and I use our approximate way of counting when we scatter only on the Majorana fermions near the bottom of the data column. And then basically what we do numerically, we now do the calculation on a finite size system. So we can do the calculation, single value decomposition can be done in a very large system. And so it's 500 by 500 by 2. And then we can see what the Fermi-Dirac distribution, how that would modify the scattering. And by this, we can actually check how our diagonalization on the real space, how it compares with our analytical result. And you can see that overall, so once again, the shape of this anisotropic scattering is actually preserved. And what you see that the scattering at very low temperature is very small. So you need also to see to the scale bars and see that the scattering is significantly increased with the temperature because the thermal occupation of the low energy states is actually increasing. But still, this calculation is artificial because we are going to the large temperature, but still consider the zero flux sector. So the idea of this calculation is basically to see what is how the fermionic degrees of freedom, the contribution from the fermionic degrees of freedom is changing with the temperature. And here again, it's only the particle Hall processes are included. Okay, so when you see this, you see that intensity is including, but this 6-4 anisotropy is remain. And also remember how it's oriented. So now this is more important. So now we actually do the true calculation. We consider the thermal flux sector, and therefore the constraint of moment conservation is relaxed. We have only the energy conservation. So in that case, we can have the contribution from both particle-Hall processes and particle-particle processes at finite temperature. And we can plot this is basically how the imaginary part of polarization bubble as a function of the phonon frequency is changing. And you can see that at very low temperatures, you only have a particle-particle contribution because particle-Hall contribution is very slow. But then when the temperature is increasing because of the thermal population of Majorana fermion states, you see that this particle-Hall contribution is increasing. What I shaded here, so basically this is just once again the plot, but in fact one needs to remember that our elasticity theory works only for small q and therefore for small omega. So in fact, the rest of the spectrum is kind of artificial, and we need only to consider this low energy part. And we see that with temperature, the contribution between particle-Hall and particle-particle are changing, and the particle-Hall is actually increasing with the temperature. Okay, and here is the result. And what you see immediately that this structure of the response. So once again, here the blue lines correspond when you have no scattering. So these are particular direction where you have no scattering, and all this colored plot is when you do have scattering. And I didn't say this, but on the horizontal and on the vertical axis, what we plot is just Qx and Qy. This is nothing else as a phonon momenta in a small part of the brilliant zone. So this is from 0 to 0.5 pi of the brilliant zone. So it's a small part of the brilliant zone near the zone center. And once again, what we see is that this shape in the presence of the fluxes is quite different from what we had in the zero flux sector. And once again, let me say that the thermal flux we sample with the help of the Monte Carlo. So because of the Monte Carlo calculation, of course, we cannot go here for such a big lattices as we had before. So the calculation is done on the lattice 32 by 32 by 2. And these are the results. And what you see that when the temperature, so you have still this C6 symmetric anisotropic shape of the scattering. And when the temperature is increasing, it's become more and more symmetric. And what is important also, that around the zone center, the Majorana fermions, they are basically are not involved. So these phonons are basically remain almost not scattered. So the biggest scattering for the phonons are with the biggest energy, once again, because more processes can be stimulated by more energetic phonons. But this is the result of the temperature evolution of the sound attenuation for the case when the Fermi velocity is larger than the sound velocity. And we believe that some sort of the pattern like this can be observed in the experiment. One can, I mean, of course, it's much more easy to do theoretically than experimentally, but we believe that some anisotropy at this particular angular structure can be observed by experiment. So this is about sound attenuation. If you have questions, so let me answer to this question. And what I'm going to discuss about the phonon Hall viscosity. This is another observable, which can be done when the time reversal symmetry is broken. Okay, so how I'm doing with time? So
you have about 8 minutes.
Okay,
we're going until 3 or 4. Yes.
Good. So Hall viscosity. So let's go back to the origin. So how we discuss the viscosity. So if we want to relate the stress tensor to the strain tensor, then this coefficient which goes there, it's elastic moduli. But if we want to relate the stress to strain rate tensor, then that would be this viscosity tensor. So what is important is for non-interacting phonons. So first of all, it should be anti-symmetric one. And second, what is important that for non-interacting phonons, this viscosity tensor should be 0. And it should be some interaction, either phonon-phonon interaction or interaction of phonons with other degrees of freedom when this tensor become non-zero. So this tensor can be separated in two parts. One would be the symmetric part, and what enters here in the symmetric part will give rise to the dissipative process, because in order to have dissipation, you need to have a symmetry, and that comes from the causality principle. And then it will be the antisymmetric part, and the antisymmetric part cannot contribute in dissipation. So basically, that would be the non-dissipative contribution in the Hall viscosity. So quantum spin liquids and also quantum Hall fluids, these are the system where we can really observe this non-dissipative response, because if you go to exactly t equals 0, then the symmetric, eta s, so this symmetric viscosity tensor should be, this component should be equal to 0. But this antisymmetric component, it may vanish or may not vanish at 0 temperature. So therefore, if you have this time reversal symmetry breaking and you have a gap, so for example, like in the Kitaev model in the time reversal symmetry breaking, then at temperatures below gap, so at very low temperatures, this contribution from non-dissipative processes can dominate over the dissipative processes, because these processes in the gap should be equal to 0. So there is a temperature range where there is a chance to observe the contribution from the whole viscosity. Okay. So, and that once again, at very low temperature, the viscosity tensor can be dominated by this non-dissipative part. So now it's about our Kitaev model. So we were discussing the action for phonons, and now that would be the contribution to the action from this viscosity part. Okay. So now what we need to know, so if this eta A is non-zero, but also how many independent components we can have for this viscosity tensor. And one can actually show that it will be, from the symmetry analysis, it will be just one non-zero component for this tensor, and that can be explained from the symmetry ground. But what is the most important, that when you have a time reversal symmetry breaking term, it's actually lowers the C6V symmetry of the lattice to C6. And in this case, you can find this antisymmetric A1 irreducible representation. So there is only one non-zero contribution in this tensor. Okay, so now when we know that it's only one component, once again, using this symmetry analysis, we can write what is this antisymmetric contribution to the phonon action. And once again, you start with the strain tensor expression and the strain rate tensor, because this is, once again, it's coupling of the strain to the strain rate. And then you quantize your phonons, and you do exactly the same thing what we were doing for the description of the phonons in the case of the time reversal symmetry. So we have this action, and once again, the presence of the phonon Hopf viscosity can be related to the Berry phase coming from this chiral H mode of Majorana fermions when we have kappa not equal to 0. And then the way how the whole viscosity can be computed, in the usual way, you can use the Kubo formula. And if you use the Kubo formula, then you can show that this kappa H can be related to imaginary part of the off-diagonal terms of this polarization bubble, or phonon polarization bubbles. So far we were discussing the contribution from diagonal components, and now we are looking for the contribution from off-diagonal components of this polarization bubble. Okay, so once again, this is the expression, the theoretical expression. Again, we have this two green function, two product of the two vertices. If we are at very low temperatures, or at temperature equals 0 in this case, then we can use fermions with the wave vectors, with the momentum quantum number being a good quantum number, with wave vector being a good quantum number, and we can do the calculation. What is important is that this off-diagonal element is proportional to the size of the gap, which is proportional to the kappa. So once the gap is closed, then basically our Chern number is going to 0, and therefore all of this is going to 0. Okay, so another important thing, because this one is antisymmetric with respect to change of the indices. So in this case, one can show that both high energy and low energy Majorana modes contribute. And in fact, you should not just look at the vicinity of the Dirac point. So you can do the first estimate by taking the Majorana fermions only near the Dirac points, and then you can do the linearization of the spectrum, but the full result should come from the whole spectrum. So this is very important. And once again, you need to have this anti-symmetrized. So this component, you have to have everything anti-symmetrized. So this is the result. Once again, the dominant contribution comes from E2 channel. And what is important, that this imaginary part depends on the sign of kappa, so it will change sign if magnetic field will change sign. And also when we integrate over the whole Brillouin zone, there will be some function, so R of k, which will depend on the kappa like this. Okay, so it actually will be decreasing with the kappa, and so basically this contribution will decrease with the kappa. Okay, so what is also important that the imaginary part of this polarization bubble is odd under omega. So you see that here it is proportional to the frequency. So if you change omega to minus omega, that should change sign. So and that actually shows that we are dealing with anti-symmetrized imaginary part. And then once again, when you have this, you can write how the whole viscosity coefficient will depend on this parameter. So this is the approximate expression when we still consider very low temperature, when flux contributions are not giving any, that we can use still the zero flux grounds sector. Okay, so knowing this whole viscosity coefficient, we can also compute the phonon thermal conductivity, and basically that is proportional to this eta h, the expression which we have here, proportional to T cube. So what you see here that the whole viscosity, this eta h, is not temperature dependent. It doesn't depend on the temperature, and it doesn't directly actually depend on the nature why the time reversal symmetry is broken. It depends on the sign, and it depends on some numerical quantity. It basically depends how the spectrum of Majorana fermions is in the whole Brillouin zone is changing with respect to kappa. Okay, so now once we have this, we can see what would be the observables, and the observable would be the change in the phonon spectrum. So now we need to renormalize our phonon propagator. In this case, we have to rediagonalize this, and what you get is this expression. So you have this linear of Q contribution, the first contribution which we get when kappa was equal to 0. This is our linear spectrum, longitudinal and transverse. And then you see that there are corrections, the Q cubic correction to this spectrum. And then you see that this correction would be actually having different sign for longitudinal and transverse mode. Because if VS transverse is smaller than VS longitudinal, then this number would be negative, and for the longitudinal it would be positive. So basically, if you look to the phonon spectrum, you would see that it will be curving out. So basically, this linear dispersion will be changing, and these branches will kind of curve away from each other. And one can actually compute some characteristic Q vector at which this curving is starting, which will, of course, depend on this ratio of the velocities and so on. So these are the low temperature results when the zero flux sector is still a good sector. And okay, here is this expression for this characteristic dimensionless quantity from which we can see the curving of the spectrum. So this, once again, the curving is coming from the fact that longitudinal and transverse mode are now mixed due to the presence of time reversal symmetry break. So, and next thing what we do, we actually look what is the temperature evolution of the whole viscosity, because once again, in our calculation so far, that was temperature independent. And we do exactly as we did before. We are considering at each temperature a different thermal flux sector, which we sample with a Monte Carlo. And for each of this sector, we compute the eta h, and then we average over all different distribution. So what we get is two things. So on the left, I show the dependence of this on the kappa. And you see that this dependence on kappa is actually is temperature dependent. So if you are at a very low temperature, then you see the dependence on this kappa is more or less similar to the results which I showed before. But when the temperature is growing, the dependence on kappa change significantly. And that comes from the fact that in non-zero kappa, so when the time reversal symmetry is growing, one can show that the flux energy, so the energy which goes to excite the flux, is actually getting smaller, and therefore you have less pronounced dependence of eta H at higher temperatures. And on the right, you see the eta H plot as a log of temperature, just to see the features more precisely. And basically what you see here is that when kappa is increasing, so in any case, whenever temperature is increasing and the flux are proliferated, then this kappa H is disappearing. Okay, so with increase of temperature, the kappa H would be smaller and smaller, and this is actually coming from the fact that this gap, which was protecting this chiral state, the gap in the bulk of Majorana fermions, which was protecting this age Majorana fermions, is actually getting smaller. So in any case, the result is that the whole viscosity decreases when fluxes proliferate. And this is also the dependence on this strength of the time reversal symmetry breaking term. So I'm done. Oh, so one more thing, maybe less important. So the other effect due to Majorana fermion coupling is that the Majorana fermions in the pure Kitaev model, they have infinite lifetime. And basically what we did for the phonons, we can also compute the back effect from the phonons to the Majorana fermions and compute self-energy for the Majorana fermions. This is the Feynman diagram, which corresponds to the self-energy. And basically what we found that the self-energy is proportional to T squared, so it's smaller than the typical fermion energy, which is proportional to T. And therefore, there will be some correction to Majorana fermion lifetime, but they will be small. And that is important when people are thinking about exploiting these Majorana fermions in a quantum computation. When you want to kind of move them, to do some braiding of them, you need to know how long they live. And basically the answer is, and actually we also did this calculation at when the time reversal symmetry is broken, so in finite kappa. So nevertheless, these corrections are always small. So those who are interested in quantum computation, maybe Kitaev materials are still a good system to work. So here is the summary of my talk, and let me not read it and say like in 2 words. What I wanted to show that now we have a theory how to compute from microscopic ground the coupling between the Majorana fermions to phonons, both in the zero flux sector and in the presence of the fluxes. And there are observables like sound attenuation, Hall viscosity, and probably there are other observables which, if you measure them experimentally, then they can learn. You can learn something about the properties of underlying quantum spin liquid. Thank you very much for your attention. So please, if you have some questions.
Thank you very much. That was a very wonderful talk. So yeah, are there any questions? I don't see anything in the chat.
I would have a question.
Mm-hmm.
Yes, I was a bit confused in this sound attenuation story when you showed the Dirac cones of Majorana fermions, and you were referring to the occupation of Majorana fermions. How do you specify that? Because I think you need to pair Majoranas first to a complex fermion and then think about its occupation. So what do you mean there?
Okay. I guess you are asking from
in the attenuation.
Okay.
Yes,
so
those figures.
Maybe we can look here. Okay, so okay, so what you need to do, so you can think about the spectrum for Majorana fermions, or you can think for the spectrum for complex fermions. So basically, if you want to think about the complex fermion, then you just need to have you need to get rid of all the unphysical states. So basically, you can just consider all the states with the positive energy, okay, to some extent. So the way how you can do, you can first take the Majorana fermions and form the complex fermion, and then do everything, they propagate everything in terms of the complex fermions. So in that case, maybe you should talk about not scattering of the phonons on the Majorana fermions, but on the complex fermions which are formed from combining the Majorana fermions. But the origin is still this Majorana fermion itinerant excitation of the Kitaev spin liquid. But once again, you can think about this. You have like 2K point, how you get rid of the additional states, but you can really think about this as complex fermion Dirac codes. So I think it's more subtle when you discuss this particle-particle or particle-hole, what you call particle-hole for Majorana fermions, if particles and hole are the same. So in that sense, this language works much better if you first go to the complex fermions, and then you can really say what are holes and what are particles, and this discussion of the different contribution, as you said, it's better to discuss in the complex fermions. But you start with Majorana fermions in any case.
Okay, thanks.
Any other questions?
So yeah, okay, can I ask a question?
Yeah, go ahead.
So hey Nasha, this is Mehdi. So the question is about the phonon polarization. If I'm not wrong, in most cases you ignore the vertex correction. Is that correct?
Vertex correction to what?
To the polarization function of the phonons, you know. You can also add the lines to the vertexes, to the vertices of the polarization function. I think you...
I mean,
yeah.
I think you're asking about the phonon-phonon interaction. So basically, I start with the bare phonon model, and for me, the phonons were not interacting among them at the origin. That's probably what you're asking.
No. No. You calculated the bubble diagram for the phonon polarization function, right? And but the vertices can be renormalized by the
sure, you can,
by the Majoranas.
Yes.
By the Majoranas.
So, of course, I was considering the one loop diagram without any vertex correction.
Right.
So,
and is that, yeah, okay, then the
so I think
next question
that would be justified, because the vertex correction, if you have, so we already did some approximation. Here, the smallness comes from the small q from the phonons, from this long wave limit of the phonons, and from the low energy excitations for the Majorana fermion. So basically from these Dirac cones. So
okay.
whatever vertex correction I will do, that will include the higher order terms.
Higher order terms.
In principle, of course, what you can do also, that I thought that what you are asking is that you can start with the situation that you take also the unharmonicity, phonon unharmonicity into account, and then couple to Majorana fermions. But once again, for the same reason, that will give only a small correction to the result. The result will stay.
I see. Okay. Thank you so much, Nasha. Thank you.
One more question.
Mm-hmm.
So in this discussion, you included the effects of acoustic phonons.
Yes.
So what would be the role of optical phonons, or is there like a reason why they wouldn't affect this physics?
I mean, if you think, so I think the story about optical phonons in Kitaev spin liquid is very interesting, but it's for different type of experiments. For example, you can try to understand phonons in Raman scattering. Okay, so you can have some shape, final shape of the phonons in the Raman scattering, which would be coming as a result of the coupling of the optical phonons with some continuum of excitation. Here, it's really sound is a. If you think about sound, sound is acoustic mode. Okay, so and basically you just the experiment which we envision is that you have some transducer and then you pump some sound waves, which are acoustic waves, into the system, and you see how they scatter. So in that case, you don't need to think about optical phonons. So in what we discussed here, that was all about the low energy phonon modes. Once again, I think optical phonons will couple to Kitaev spin liquid as well. And we are thinking, and we start doing some calculation. And actually, in this list, So this phonomagnetic effect, which we're thinking about, it's completely based on the optical phonons.
Okay.
So, but I don't have yet results to show.
Okay, thank you.
Okay. Any more questions?
I would have one more question. It's a bit speculative. So you have a 2D system of Majoranas. So if you take out the phonons for a moment, you have a 2D system of Majoranas, and if you're at finite energy, finite temperature, it's disordered. And I think such a system in principle can show interesting localization physics. So there could be a stable thermal metal phase in an insulator. I don't know if that's the case in your system, but the question is it? Does this physics happen for the Majoranas? And if yes, can you probe it with the sound attenuation?
It's a very good question. So yes, I mean, in principle, one can think about, so there are two different effects. So one effect is that when you have some disorder in the system, so it can be the thermal disorder simply coming from these fluxes, the thermal disorder is not leading to localization effect in the Majorana fermions, but instead it's leading to some like Lifshitz there with some sort of localization, but it's still kind of weak. But you can think about the system in the presence of some other quench disorder. So if you have the presence of quench disorder, vacancies or bond disorder and so on, and then you try to think what is happening when you couple to the phonons, then I do believe it will be interesting. One thing which we plan to consider is that when you have vacancies, since we studied them already, we know that there is a piling up of low energy states due to the presence of vacancies. So also this kind of constraint in this presence of vacancies, the constraint which we use is destroyed. And basically you are effectively going to the limit where you have a lot of the density of states for low energy Majorana fermions is very large. So, and clearly then the scattering of the phonons, this attenuation of the phonons will be significantly enhanced. So then in that case, you have this non-monotonous temperature dependence of sound attenuation with the temperature, because your density of states shows this non-monotonous behavior as a function of energy, then you will be able to see this. That's what we are trying to compute. But this thermal metal, yes, it's a slightly different story. There was some works in the presence of different like flux crystals that was discussed by Simon Trebs and by Matthias Voigt. So I think if you will manage to realize this system physically, then of course its coupling to the phonons will be very interesting. But I think you first need to have some means to have this state. And for me, it's still not completely clear how these states can be realized. I mean, theoretically, yes, but in real materials, it's probably a little bit more complicated.
Thank you.
Okay. Any more questions? All right, if not, then Natalia, I'd like to thank you very much. It was a very fascinating talk.
Thanks a lot for listening.
Yeah, no problem at all. And I guess we shall see you all next week.